Okay, so let's get started. Couple announcements. So there is, as I mentioned, no class next week on Monday. I'm traveling, so I will have a makeup class the week after. I'll send out an announcement about that. And then the next two classes after Monday's class are going to be guest lectures. So one is going to be on green computing and one is going to be on multimedia, audio, video streaming. Okay, and then once the guest lectures are done, we'll continue some of the final few topics that are still pending. Okay, so I'm going to today finish a couple of overflow slides on cloud computing from last time, and then we'll spend much of the class today on web and caching and consistency. Okay, the material we covered on the cloud and caching consistency, all of that is going to be somewhat relevant to the final lab, which is why I'm actually doing them out of order, getting the material done before the final lab, which will be out after this lab. Obviously, this lab is still not due until later this week. Okay, so that's the reason for doing these couple of topics a little out of order. So let me finish the discussion on cloud. If you remember, I was talking about different types of cloud: infrastructure as a service, platform as a service, and software as a service. And I mentioned Google App Engine as an example of a platform cloud and EC2 as an example of an infrastructure cloud. Okay? The next homework is actually going to be a cloud computing exercise where you will do something on EC2 cloud, some simple exercise on EC2 cloud. Okay? Now, so another way to think about clouds, whether regardless of the type of the cloud, is whether they're public or private. Okay? Pretty much all of the discussion we had in the last class focused on what are called public clouds. A public cloud is one where the end users of the cloud as well as the owners of the application can be anyone. Okay? So it's basically a cloud available for renting resources to pretty much anyone who is willing to lease and pay for those resources. Okay? In the Amazon example, for instance, so you basically all you need to do is have an Amazon account. Okay? And then if you have an Amazon account, you can, rather than buying books or whatever on Amazon, you can say, give me a server. Okay? And then they will basically charge you for that stuff. So anyone can go and request resources of that cloud, and then you can use those resources to do whatever you want to accomplish with those cloud resources. So that class of clouds are referred to as public clouds. Okay? Now, private clouds are essentially clouds that are run by companies for their own internal use. Okay? So large companies have lots of end users, and they may just want to deploy a cloud service for similar reasons. But that cloud platform is only open to users within that company, not people outside. So you think of it as the IT department of a large company runs a cloud service. So you can think of UMass as an example, running a cloud service to all the departments, faculty, and graduate students. So if you're a student, you need a machine for your research, you could go to this kind of a cloud, internal cloud, and say, give me a server, rather than going to Amazon. So since users of a company also need computational resources, the cloud model has been adopted by companies for their internal use, and such cloud platforms are referred to as private clouds. Okay? They look more or less similar to whatever public clouds do. They can give you server, storage, all sorts of resources, except that they're not open to others. Okay? They're only open to users within that enterprise. So these are the two types of clouds. Now, you hear a lot about public clouds, but private clouds are actually also quite popular. They are run by companies, but since they are close to outsiders, you don't actually hear or know too much about them. Okay? But they are becoming popular. Okay, another model that is emerging is a hybrid of a public and a private cloud, whereby a company or an enterprise starts off with a private cloud that they have for their own internal users. And on certain occasions where demand for cloud resources exceeds, let's say, the amount of storage or the number of servers present on that that private cloud, the cloud platform has the ability to dynamically go and pull some resources from a public cloud. Okay? So let's say UMass, going back to this hypothetical UMass example, UMass runs a private cloud and it has 100 servers allocated to its cloud. Okay? And perhaps at some point in time, maybe it's the end of the semester, everyone is doing assignments and whatnot, and there's a lot of demand for these machines, and let's say all 100 machines get allocated to users. Okay? Now, if some more users come and demand machines, there aren't any. So you could go and say there is no resources left, so sorry, we cannot give you resources. Or what the cloud can do is it can actually, on behalf of the user, go and temporarily lease some resources from a private public cloud, let's say Amazon, okay, and then give those resources transparently give those resources to end users. Okay, in this case, you have a hybrid where you use local resources from your private cloud wherever possible, and you overflow into a public cloud whenever your resource demand exceeds, or the request for resources exceeds the number of machines or storage you have in the cloud. Okay? This is referred to as a hybrid cloud where you move resources between private and public depending on load, and there are mechanisms designed to do that. Those mechanisms are referred to as cloud bursting, where when you have a burst of workload, you actually go into a public cloud. Okay? So there are these hybrid models that are also emerging. You hear about hybrid clouds when you look at some of the press that you've seen or you see on news sites and so on. Now, the last thing I'll mention here is programming model for the cloud. There are, you can of course run any client server application on the cloud. At the end of the day, it's just a remote machine. If it's an infrastructure cloud that you lease, you can log into it and run whatever application you want. Okay, so typical client server applications run just fine, okay? But there are several new kinds of applications that are also becoming popular. One is referred to as MapReduce. I don't know if any of you heard of this. So MapReduce is a platform that is used for data-intensive processing. Okay? If you have very large data sets that you want to process, okay, let's say they are data sets from biology or life sciences, or they could be financial data sets. If you have lots of data and you want to do some processing to get some results, you can use this programming model to make that processing highly parallel. You can use lots of machines and process data in parallel rather than having one machine that has to process all of this data. Okay? So you get the benefits of parallel processing. So the programming model is such that it's inherently data parallel. So it allows you to access this data on different machines in parallel, process it, and merge the result. Okay? So these type of models have emerged and they are popular to run on the cloud. Okay? There are lots of companies that collect data for their services, and then they take that data, they put it on a cloud, and then they run this MapReduce job that process it and tell the company something interesting about the data they have collected. Right? There are many such examples. Companies like Facebook, for instance, use this kind of processing to decide what pages within their entire system are popular, what are users doing, and then they use that information to decide how to set advertising rates for pages. Okay, pages that are more popular cost more for you to put an ad on, for instance. So this is used to decide what is popular at any given time. Okay. Other companies use it to do research on new kinds of medicines. Okay, so they do lots of computations to figure out what kind of medicines might work best to cure a disease that doesn't have a cure, for instance. Right? So there are many examples of what kinds of data-intensive computing applications are out there. And cloud has become a popular way for you to basically do this, because you can, as I said, the main advantage of the cloud is you can go and release resources temporarily. You have a large data set, you can get 100 machines, process that data set, maybe it takes 2-3 days, and then you release those machines and you're done. You don't have to go and invest and buy 100 machines, which is going to cost a lot of money. Right? So if you have temporary needs, using the cloud to do this kind of processing is actually much more beneficial than having to spend a lot of money buying those resources yourself. Okay, so that's the programming model. There are many challenges that arise. We started with data centers and we're talking about clouds, but as you can imagine, cloud platforms actually run on data centers. There are interesting issues that you have to deal with when you design a cloud platform to run on these data centers. Okay, so there's privacy and security, which basically says how do you guarantee isolation between client resources. There are many applications, many independent customers who may be running their applications on the cloud. You don't want one customer to impact other performance seen by other customers on the cloud. Then the other customer becomes unhappy. Right? So you want to be able to isolate the resources that are allocated to customer A from the performance seen by customer B, independent of what customer A is doing. Okay? Maybe their resources are overloaded, maybe they are not. You don't want others to see an impact. Okay? So OS level resource or hypervisor level resource isolation mechanisms are important. There's of course security. Right? So you basically don't want somebody's machine got hacked and that is impacting other customers on your data center. You don't want that. Okay, remember that in the cloud provider owns the machine, but they have allowed control of the software to some third party who's just paying you for them. Okay? So it's effectively they have administrative level root access to those machines. If they don't administer the machine well, it is likely to get hacked by malicious users somewhere. Okay? And you don't have full control over this. So in some sense, you don't want some incident like that to impact other customers that may be well behaved, for instance. Right? So these are hard problems to deal with. Okay? So those are all interesting questions that arise. Okay, there's the issue of scalability. These cloud platforms are very large. So you have to ask the question, how do you manage, let's say, hundreds of thousands of machines? How can you automate some of these tasks? And then programming models. As I said, you have lots of data parallel or compute parallel tasks. What programming models make sense in this context? So these are all interesting questions. Many of them are open questions. It's not like there are answers that people are still doing research in this area. So if something like this is of interest, then you should read some of the papers to understand what people have done in the research community, what are open questions, and so on. Okay. So that's basically the overflow slides from cloud. And what we are going to do now is switch gears and talk a little bit about a different case study, which is going beyond the World Wide Web. Okay, so this is the second case study. So I'm going to quickly, there are two parts to this case study. First, I'm going to talk about servers and web servers and proxies and clusters and all that kind of stuff. And then the second part is going to actually be looking at web caching and consistency. So if you remember the discussion we had on cache consistency models, I said at that point, I said those are abstract models. I did not talk anything about implementation at that point. And I said we'll come back to a case study in the web and then we'll look at how can you implement cache consistency models in a specific context. Here we'll talk about the web and you will see how you can do strong consistency, weaker forms of consistency, all the ideas, not all, but some of the ideas that we talked about, how do they get instantiated. So this is an instructive case study to keep in mind. It's also useful because you may actually end up using some of these ideas for the last lab, which involves some form of caching and cache consistency. Okay. So this is the picture to keep in mind. Okay. So this is the web is a client-server system where the client is essentially a machine that runs a browser that is accessing content from a remote web server, and there can be any content that this web server serves, whether it's static HTML pages or dynamically generated pages. We'll look at all of that. Okay. So the assumption is this web server is accessing content that's stored on a disk. Okay. It could be files or it could be content that is coming out of a database that the web server is then going to construct a page and send back to the user. Okay. So standard client-server system, the client is the browser, the server is a HTTP web server. Okay. So here is sort of, if you just look at the server, not the client at the moment, okay, you will see that the server itself is not one logical entity. I talked about multi-tier web servers a while back in the course. We're going to revisit that a little bit. Okay, so there are multiple tiers to standard web application. There is a front-end web tier. Okay. There is a middle tier, which is basically the application itself, and there is a data tier where the data is stored on disk. Now, typically the front-end web tier is an HTTP server, because the standard protocol for accessing any web content is HTTP. So this server is a HTTP server. It could be Apache or IIS or any of these services. Okay. This second tier is where you write your application code. Okay. Let's say you want to set up a bookstore, an online bookstore where you have a catalog users come in, they search for products in that catalog, and then they put some kind of products they want to buy into a shopping cart, and then they go do a checkout. Standard stuff that you've seen in any e-commerce site. All of the code to do that is actually written in what is called the application tier. Right? Applications can be written in a variety of different ways. Okay? What this figure is showing is that you write the application as a CGI bin process. This is actually a figure taken from the book. This is not the common way today people are writing applications. You can write that application in Java if you use Java servlets or J2EE. Okay? You can write that on Python if you use a Python web framework. You can use Ruby on Rails, which is another web framework. You can write it in PHP. Right? PHP is a very common language that you use to write code for your application. So any of these languages can be used to write the application, and this is where the code resides. Okay? Requests will come in over HTTP. The HTTP server will simply hand those requests to the application tier. The application tier will process that request and do whatever it needs to do. In many cases, to service that request, it may actually have to go to the database, retrieve some content, and construct a page. Okay, so if you actually send, let's say this is an online bookstore, and you may be searching for books by an author, let's say Tannenbaum. So you will send a search query over HTTP. Okay, that's a browser form that you will submit. It will come to HTTP. HTTP will hand it to the application tier. The application tier will take that search term and it will actually construct a SQL query and search the catalog, saying show all the books in the catalog that have this author. Right? And some records will come back from the database. Right? You will take those results and you will on the fly construct a web page saying here are the results. Here are all the books we sell that have Tannenbaum as the author. You will construct a web page on that for on the fly, because this is not a pre-stored web page, like it's not a static HTML page, this is called dynamic HTML. Right? So you construct that web page, you hand it back to HTTP, HTTP constructs a response, sends it back to your browser. Okay? This is how this kind of application. So then you may decide to buy a book from the catalog or in the search result. When you hit buy, then another request will come with a buy, and then basically there will be some state created here for a shopping cart. That item will be put in that shopping cart, another page will be constructed, it will be sent back, and so on. There will be multiple interactions between the browser and this web application. This is referred to as a user session. Okay? And so you may end up then saying buy, and you present your payment details, credit cards, and whatever. So all of that is again handled here. Okay? So this is the most complex. The application tier tends to be the most complex part of a typical web service or web server application. Okay? And then the database, of course, has all of the data for the product catalog, all the purchases made, all the user account information, all of that is stored in the database. Okay? Any questions on this? This is a picture to keep in mind. It will be relevant for some of the discussion that is coming up. Okay. So that's the multi-tiered architecture. Now, typically, this is another way to think of web servers, is typically if you have a very large website, then each of these components here will be replicated. There will be multiple copies of it. This is logically shown here, where you have basically multiple copies of that web application. Each of those could be a multi-tier site. Yeah, this is just shown as one logical box, but they could actually, each tier can be replicated. This is not showing tier replication. So what happens in that case is there is basically a front-end node that is basically presenting itself as the website to end user. Okay, so browsers connect to this front-end node. Okay, so this could be, let's say, www.amazon.com is this node. Okay. Behind this node may sit 100 other nodes that are actually all replicas of the application. Okay. So requests come into the front-end node. The front-end node is essentially a load balancer. It's called a dispatcher. Okay. It's going to take that request and hand it to one of the many replicas, saying go start servicing this request. Okay. And then that web server will then actually take the request and process it exactly in the way that I talked about in the previous slide. Okay. So think of this as the load balancer. Requests are coming in, and the load balancer is split those requests and assign them to individual replicas. Each replica is actually going to go and service those requests. Okay. Now there are many subtleties. This sounds very straightforward, but there are many subtleties you have to keep in mind. Okay? Because users have active sessions. Let's say you are in the midst of buying a book Okay, and you put that book in a shopping cart. Okay, that shopping cart is state that the server has maintained. Okay, so if previously the request was assigned to this replica, the state of the shopping cart is actually assigned there. Okay. If then you say actually press the buy button and another request gets generated, if the load balancer sends it off to a different server, that server will not have that previous state. Okay, because the state of the shopping cart is on machine 1, the subsequent request has been sent to some other random machine that knows nothing about what has happened so far. Okay. So what that tells you is that this switch has to be stateful. It needs to keep track of if this user has previously sent a request, which server did I map that request to, and any subsequent request from that user has to be actually sent to that server. Otherwise, if you send it to some random other server, any state information for that user session is going to be lost. Right? So this is a stateful load balancer where you are load balancing on a session basis. Once a new request from a user comes in and it gets assigned to a server, for the duration of that session, you have to only send that request to that server. You can't send it to another server. Okay. So this makes load balancing harder. The system becomes stateful. There are lots of complications one has to deal with as a result. Okay. So here is another peek at this switch that I was talking about. Is itself actually not one but multiple components. There is a switch. Okay, this is sort of which accepts an HTTP request. Okay. And then there is basically what is called a distributor, and there's a dispatcher. Okay, so basically, the first time a request from a new user comes in, the dispatcher is the one that decides this is the machine that is going to actually service that request. Okay. Once you figure a map a user session to a machine, you tell the distributor saying this session is now mapped onto this server, so basically you are going to then send it to this server. Okay, so that's basically doing the distribution. Now, occasionally, the web servers also have the ability to redirect the request, that's that arrow being shown, to another replica. These are replicas of web servers. So for whatever reason, the web server may say, I don't want to do it, you handle it and you can forward it. Okay, so some of these internal forwarding can also happen. Okay. So what seemed like a very straightforward web server, okay, is actually quite a complicated system. Okay. So there is a switch, there is load balancer, there are replicas, each replica itself is distributed into multiple tiers, there are databases. So to set up a system like this, as you can imagine, is quite a complex task and get it to work and so on. Okay. So just to give you some example of what happens when you have very large websites. None of this complexity is needed if you want to set up a small site. If you want to, that's good enough. You search to set up Apache, maybe your content is all static and you're done. And even if it's not static, you have one machine where you're running PHP and the database actually runs on that server and you're done. Most small websites use a single node. Most large websites may use large number of nodes. That's why things get very complicated quickly as you start scaling to more and more machines. Yes?
So in this example here, would you have a dispatcher in which in each web server that would either stick with the request or hand off to another one?
Yeah. You're saying why does that happen, or are you asking is that what happens?
No, it was just the second.
Right. So the dispatcher is simply, this is where the load balancing algorithm is implemented. Mm-hmm. So new requests come in, you have to ask the load balancer which replica should service it. What this is simply showing is an example where the switch randomly chose a web server and sent it here. The web server says, I ask the load balancer who should service it. Okay. In this case, the load balancer probably chose that other server, so then the distributor here just forwarded it to that server. Okay. So that's what is being shown. You may not set it up this way. You may actually have the switch and the dispatcher be implemented as one entity. So as soon as a request comes in, you ask a local load balancing algorithm, what should I do, and directly send it to the right server. Okay, in this case, this is not the way it has been set up. Yes.
What's the advantage of splitting it up like that?
What is the advantage
Yeah,
of
why would you have it on two separate machines like
the dispatcher?
that? Yeah.
Right. So typically the question is, why should the switch and the dispatcher be separate? Okay, so the reason for that is typically the dispatcher is a load balancing algorithm that application developers write. Saying this is the way I want to balance load for my application. Okay? So there is some application logic involved. Are your requests stateful? Are they not stateful? Do you want to do least loaded first? Do you want to do some other random hash of the request and decide how to do this. So there are many application level things that you have to keep in mind when you implement this load balancer. Right? This switch is a pretty standard request forwarding switch that you can just buy from a company like Cisco that really has no intelligence as far as the application is concerned. Okay? So if the switch were programmable, you could write your load balancing algorithm using your favorite language and deploy it on the switch. Okay? But if the switch, typically switches are not programmable, so what happens is you just make this a standard server of some sort that runs your load balancing algorithm. Then you need to separate them out. Okay? That's basically the reason. Yes, your question.
So how about the client just communication with dispatcher and catch the needs and just communicate with the web server directly, just similar to DNS?
Yes. So question is, can the client also do this? Maybe the client will actually, you basically, if you could do load balancing at a DNS level, this is internal load balancing. This is transparent to the client browser. Okay, browser is just seeing the switch. Okay. You could also expose that to the browser where you have these replicas have real IP addresses and you have a DNS record that basically has that entire list, and you're doing what is called round robin DNS. I showed this when we talked about DNS. Okay. So what happens is every time a new browser resolves it, you will be given one of these IP addresses, you directly talk to those machines. In that case, there is no switch at all. Okay, browsers are directly talking to one of these replicas. So there are many, many different ways to set it up. This is a pretty standard way. Round robin DNS is typically done if you have what are called geo-replicated applications. Right? If you have one replica in, let's say, East Coast, one replica in West Coast, and you want all the East Coast users to come to the East Coast replica, and the West Coast users to go to the West Coast replica, you don't have a switch. Right? So this is assumed that this is all happening on within a single data center. Okay? In that case, you are better out doing the load balancing using DNS. Okay? Because if you send it to the switch, the whole point is you want to reduce latency. The switch is a centralized component. All requests have to come here and then sent out to the West Coast. It doesn't help with the latency. Right? So if you have really geographically distributed applications, you use DNS to load balance. If application is distributed inside a data center, you use a switch and a dispatch. There's so many different ways to set it up. Yeah.
Can you actually use DNS to make sure it goes to your closest data center?
Yes. So you could have each of these. The question is, can you use DNS to make sure it goes to the local data center? You need intelligent DNS. If you use plain old dumb round robin DNS, it will just cycle through a list. It has no intelligence at all. Okay? But you can actually embed that intelligence in the DNS, where when a request comes in, DNS actually tries to figure out, it does what is called geolocation, IP geolocation. So it tries to figure out, map the request, the client browser IP address to a location. Like, where did this request come from? And you say, okay, it came from Massachusetts. And you ask, where is the closest data center to Massachusetts? And then you map it. Okay, so that algorithm can be implemented in DNS. Okay. Again, that's not vanilla DNS doesn't do that. If you do that in your DNS, you have to write your own code that runs, sort of is integrated into DNS. Right? So these are all intelligent services you can build. So, but that has been actually done. Content distribution networks do exactly that. Actually. Okay, they have an intelligent DNS that they have implemented. They are not using the standard ones. If you use standard, it's not going to have any intelligence. It's going to do a round robin. Okay. Any other questions here? Okay, so that's the clustering part of the web. So now we looked at a little bit about how web servers work and so on. Now let's look a little bit with protocols and standards and so on. Okay, so HTML is sort of a standard that is used to sort of encode all the web documents. Okay. This figure essentially shows you HTML is a markup language. Okay. I presume you've seen an HTML file of some sort. So this table shows the various kinds of objects that you can have within an HTML document. Okay. So you can have plain text, you can embed images, you can embed audio, video, you can actually have applications, you can have PDF documents and so on that you can download. You can have what are called MIME level encoding, where any arbitrary objects can be encoded. Typical web page will have some text, it will have some images, and maybe it has some multimedia content. Okay, but that's not required. You can have all sorts of fancy things in there, which is all part of the HTML standard, but maybe some parts are not as widely used. Okay? So typically you will have this kind of HTML files that will encode these objects. Okay? So the web browser is going to first go get the parent HTML file. Then it will parse it to see if there are embedded objects. Maybe there are some images, and each of those images has to be fetched. And then depending on what HTML tells you, you will render it in the right way. Yeah, HTML documents can tell you how to render each object, where to place the text, where to place the images, what color or size the text should be. All of that is encoded in the HTML. Okay. The HTML has also evolved over the ages. You've probably heard of HTML5, which is, I think, the latest version of HTML5, which has encoding for audio video objects can actually be embedded in the HTML document. You don't need plugins to play. Any browser that is HTML5 compliant has to have built-in audio video players. Okay, right now it's basically a hack where you have this external plugin that gets loaded, and then that is used to play out that embedded object. In HTML5, it's actually inherent to the standard, and browsers that support it have built-in players and so on. Okay, so HTML has also evolved. Most of the HTML today is still HTML4 or 4.2, okay, but 5 is actually out there, and some systems and browsers already support it. Okay? That's how web documents are encoded. The way web documents are fetched is through HTTP, okay? Hypertext Transfer Protocol. This is essentially a protocol that runs over TCP. Okay? This is a protocol that your browser talks to with the web server. Okay? So to set up a connection, you essentially set up a TCP connection between the client and the server, and then the browser sends HTTP requests from the browser application to the server application. Okay, so there is a HTTP connection. Okay, there are different flavors of HTTP. Okay, typically, there are two, HTTP 1.0 and 1.1. HTTP 1.0 essentially says for every object you are fetching from the server, start a new TCP connection. Very standard. You want to fetch anything, whether it's an HTML file, whether it's an image, you first set up a TCP connection. Over that TCP connection, send an HTTP request, and I'll show you some HTTP requests in the next slide. Okay? And then fetch the object and give it to the browser. Okay? And once you fetch the object, tear down the connection. Okay? This is referred to as non-persistent HTTP. The lifetime of a HTTP and TCP connection is essentially only going to be spent on fetching one object, and that's it. Okay, if you first get an HTML file and it has 10 images embedded, you have to set up 10 new TCP connection, one to fetch each of those images. Now, what HTTP 1 did is it has what is called persistent connection. Okay, so rather than setting up 10 connections between the client and the server, which is actually wasteful, you can use the same TCP connection to fetch additional objects. There is no reason after you fetch the first object to tear it down. Okay, so what HTTP 1.1 does is, the first time you connect to a server, you set up a TCP connection. And then you can send multiple HTTP requests over that single connection. Okay, maybe the first request says, get me the index.html file, the head file. Okay, then the browser parses it and says, I need to now fetch 7 images. And then you send 7 additional HTTP requests all on this connection. And then 7 responses come back, and then you just used all of those responses to render the page. Okay. So what this has done is, by keeping the HTTP connection alive beyond the first object fetch, you are reusing the same connection for additional fetches. Okay. Yes.
Isn't this completely handled by the server logic? I saying that maintaining the connection is part of the protocol spec itself.
Maintaining the protocol. If you use HTTP 1.1,
if I'm writing my own web server, as opposed to say using Apache, I might just turn on every connection right after serving it. So,
if your protocol web server supports HTTP 1.0,
yeah,
then the browser will shut the TCP connection.
Okay, so
if you support 1.1, it's actually, this is partly done by the browser and partly done by the server. Okay? It is the job of both of these entities to figure out when to shut down the connection. In HTTP 1.0, after the response has been sent back, you said connection is done. Okay, if you want any additional data, set up new connection.
So
if you have 1.1, you will keep the connection alive.
So if my web server is tearing down the connection immediately, that's basically a violation of the protocol, and it's not.
Okay. So if your web server tears, the question is, if your web server tears down the connection, does the protocol get violated? it doesn't actually get violated because the HTTP 1.1 still lets either of these endpoints decide that they are done and tear the connection down. Okay? But typically, if the browser is interested in keeping the connection alive, because the browser knows what it is going to request next, right? So it can basically not tear it down, and the server can respect that. Okay? That's why it's mostly a heuristic. It's not a guarantee that the server has to respect it. The server could say, I'm going to tear it down. Because if there are cases where the browser says keep it alive and doesn't send any request, how long should the server wait? Should it wait for 1 minute, 10 minutes, 1 hour? Does it matter? Right? So as it turns out, it does matter. Every open socket connection consumes OS resources. Okay? If this is a popular web server, there may be millions of open sockets. You just keep letting sockets accumulate. After a while, this OS is going to run out of resources and won't be able to sustain any new connection. Okay, so you have to periodically go and clean up any open connection over which there has been no activity. If it's a dormant connection, you tear it down. Okay. HTTP 1.1 doesn't tell you an explicit rule to tear it down. It doesn't say if it's idle for 5 minutes, you're welcome to tear it down. That is left to the web server design. So Apache will have its own policy. We say if you're running out of socket resources, go and shut down some connections that have been idle. Likewise, the browser can do the same thing. I'm done, so I don't need the connection, I can tear it. So a lot of stuff is not specified in the spec, that's left to the implementation. So different web servers may actually behave differently. Yes.
So is there any advantage of using HTTP 1.0 other than avoiding the need to clean up connections?
Yeah. So HTTP 1.0, as you can imagine, there is no need to do any cleanup. As soon as you got the data, the connection is torn down immediately. So you won't get accumulation of data. Okay, but you have the overhead of setting up TCP connection. You have to ask, why does this all matter? It matters because when I talked about TCP, you remember there was this TCP SYN exchange to set up a connection. Every connection requires 3 packet exchanges. That involves latency and it was overhead. Server and the client have to do this processing. If this is a popular website where hundreds of thousands of requests are coming, think of the extra packet exchange. If you have a persistent connection, then you can reduce that overhead. Okay, so this is why HTTP 1.1 has reduced overhead. But other than that, the problem now is if you keep the connection alive, you have to decide for how long. Okay, you don't know the browser's intent. Maybe the user got up to get a cup of coffee and he or she is going to come back and then press a link to fetch additional content. How do you know how long to wait? Right? Should it be 5 minutes, 15 minutes? There's no specified answer for that. You cannot predict user behavior. Yes,
so for parallel requests, it looks like if HTTP 1.0 is better suited, like you can have lots of concurrent connections to the server.
Yeah. So question is for parallel requests, can you have multiple connections? So HTTP 1.1 can also have multiple requests in parallel if you want. Okay, you can actually send multiple requests because each response is going to tell you which request it is. So if you know you have 3 outstanding requests, when a response comes back, you can connect that to which request. Okay. So this is concurrent, it's not sequential. It's not like you send one request, wait for a response, then send another request. So it is definitely parallel. Okay. But that said, the bandwidth that you get out of this is the bandwidth of a single TCP connection. Okay. If you know anything about TCP, you will know if you set up multiple TCP connection to a server, you can hog more bandwidth. Okay. Single connection won't give you that. TCP behaves in a fair way, it allocates the bandwidth of a link across all active TCP connections. So if you actually hog and start 3 TCP connections, you'll get thrice the bandwidth of some user who's used only once. Okay. So the only advantage I can think of is if you have multiple connections, you'll get better bandwidth. Because single connection will behave exactly the way TCP behaves, it will try to be fair on the network level, and you'll get the equivalent of a single TCP connection bandwidth. So that's about the only downside, but otherwise it's generally a good thing to do. Okay. So there are lots of these subtleties where you have to decide how long to keep a connection alive. All those are heuristics. Different servers will make different assumptions. Okay, so here are the 5 methods. So HTTP is a very simple protocol. Okay, it only supports 5 types of requests. Okay, so there is a GET request. This is the standard one to retrieve a HTML file or get any object. The simplest one is GET. Put is basically where you send data back. Okay, so when you submit a web form and say submit, you essentially basically either do a put or a post. Okay, typically you do a post. Okay. Put allows you to actually send a document back to the web server. Okay. Get allows you to retrieve a document, put allows you to put a document, delete allows you to delete a document. In most cases, delete is not used. You don't let arbitrary users to delete data on your web server. Okay, although that is part of the HTTP protocol spec. Okay, so delete is typically not used. Put is used in rare cases. If you have this protocol called WebDAV, I don't know if any of you heard of this protocol. This makes HTTP behave like a FTP site. Okay, you can upload and download content. Okay, if you're essentially using FTP as a glorified HTTP, you use get to retrieve files, put to post files. You can upload files. Typically, if you're sending forms, you use a post, not a put. Put allows you to just upload an entire document. Okay? And only in that WebDAV case do you actually use delete. Okay? So if you have a web version of a Dropbox, okay, you can think of what a HTTP looks like, because that's essentially what it is doing. It allows you to upload files and download files. Okay, there are many other protocols that also use WebDAV. Okay, so very simple protocol. Okay, so there are some flavors of each of this. You will see. I'll show you some flavors of get in a little. Okay, so head just returns the header of the document. It doesn't return everything. It just returns the header. And then the get is by far the most common one. Okay. Post is the second most common one. Whenever you fill out a web form and you hit submit, it becomes a post. Put and delete are less common, only used in specific cases. So that's HTTP, and we'll see how you can use HTTP in interesting ways. Okay? So as it turns out, there is there's a set of protocols called web service protocols. This allows two web servers to talk to one another. Okay? Thus far, we've assumed that all interactions to a web server are from browsers, and there are real users, humans, that are interacting with servers. That need not be the case. You can actually have one web server talking to another web server. Okay, so that first web server becomes a client of the second server. These servers are talking to one another and interacting and doing certain things. Okay. If you set up your web site to do these kinds of things, you have essentially what is called a web service. Okay, so each of these web servers has an API that is exposed over HTTP. Another web server is actually accessing those. At some sense, the way to think about this is you are doing RPCs, remote procedure calls. One web server is doing remote procedure calls to another web server. There are many standards to do this remote procedure call. There's one called SOAP that I'll show you in just a moment. There's another one called RESTful Web Services that does the same thing. So you may ask, why is this useful? Why should one web server contact another web server and do some exchange over HTTP? It turns out this is actually quite popular. There are many sites that essentially expose one machine. Actually, this does not have to be a web server. This is an application that's independent of a browser that's talking to the machine. And users may not be actually directly interacting as they do in a browser. So there are two machines talking HTTP rather than a user talking to a server over a browser. Yeah, so you, again, as I was saying, you can ask why do this. There are many applications that are written using a web service interface. So I can give some examples, but I want to ask if any of you have ever dealt with a web service. I have an example. Yeah, you can upload to YouTube programmability. YouTube has an API. You can upload to YouTube. Okay. The search box in your browser, okay, essentially uses a web service. Right? So there are two ways. So how do you go to Google? You can actually go to google.com, then that will bring up Google's web page, and there's a key sort of box. You type a search, and then you hit submit. That is going to go as HTTP post request. Okay? But then your browser also has a search box where you can directly enter search queries. Okay, if you do that, what happens is your browser is not actually sending an HTTP request. It is sending a sort of not necessarily a SOAP, but it's sending a web service request. It's actually doing the same thing without having to get a HTML page. That's a very simple example. There are many others. If you have any client that talks to a web backend, you are essentially using this kind of service. So you could have that's a Dropbox client that you have on your machine, may be using this with the Dropbox server. It's actually talking HTTP. It basically sends requests to Dropbox. So this is how a Dropbox is going to work. Many sites basically use this kind of service. Okay, so let's say you have an e-commerce store. Okay, so a user wants to buy a product. Okay, they gave you the credit card information. Okay. What your website will have to do is then programmatically call a credit card processing site and try to authenticate the website and charge it. Okay, so there's no human sitting there saying credit card is added, let's swipe it. Okay. This is happening programmatically. So this is the bank's web service. This is maybe your web store. And you basically, or that could be a Visa or MasterCard web processing service. So your program will actually send a RPC request, a SOAP request, or some other web service request saying, authenticate this credit card and let me charge $10 to it. Okay, that's happening programmatically. Okay. So these are two servers talking to one another, because the bank's website is not going to sit on your side. It has a separate independent site. You have to write code to actually do the charging. So you can do the same thing with PayPal. PayPal also exposes an API. So if you have, you can basically send off that request to PayPal, and then PayPal will process it for you. So many examples of web services. Yeah, what I would like to show is how some of this work underneath. Yeah, so the first protocol we'll look at is called SOAP, a Simple Object Access Protocol. Okay. This is essentially RPC over HTTP. You are essentially, this is no different from a simple RPC system. It just so happens that RPC requests are going over HTTP rather than going over a vanilla socket connection. Right? So the other end has to be a web server that's receiving this request, and the web server hands it to some other system that is going to process that RPC request. So here is an example of sending an RPC request over HTTP. Okay? This is XML code. Okay, so what would happen if you send this request is you construct a HTTP request. You will send this as the body of that request and send it off. Okay, so what this request is essentially saying is that is basically the call you're making. You're calling a function called alert control. Okay, and you're basically posting an alert. This is sort of a string you're posting. So you want to send an alert message to some user. Okay, and this is going over as an RPC request. That's the name of the function. This is the string you want to post. That's the argument from the function. You basically send this over, and then a response is going to come back. Yeah, so here one client may actually send that request I showed you to another machine. The machine will process it, actually post the alert or whatever, and then send back a reply. Okay. So this is basically SOAP. Okay, it's a standard way of writing web service. Okay, it's a standard. There are systems that use it, but it is not very popular because it's fairly complicated. You can see that all the stuff that has to happen to send a simple request. Okay. There are, again, like just as in the RPC case, you will essentially write a stub. There will be a SOAP RPC compiler that will construct stub code and all of that you can link. A lot of those tools are still available, but nevertheless, it's a little complicated to write. Okay. Another way to write these RPC type systems over HTTP is to use what are called RESTful Web Services. Okay. This has become a very popular way to basically write these web services. So it's very similar to SOAP, except that SOAP is a little heavyweight. So they stripped off some of the functionality and made a lightweight version of it. And that is basically what has become RESTful Web Services. No different from when I was talking about LDAP as a simplified version of X.500 directory service, because the original spec was far too complicated. Most of those features are never used, so why implement them? Okay. So pretty much the way things work is the following. Okay. If you want to read something, you use an HTTP GET request to actually make that call. If you want to create, update or delete, you use HTTP POST request. If you want to, you can also use put to do create or delete, and use delete. So there are these 4 calls of HTTP that you will use to carry out this 4 operations, and I'll show some examples in the next slide. Okay. So the thing to keep in mind is this is much more lightweight, and it can only be used in the specific case of point-to-point, single machine talking to another machine. You can't do multi-point communication. Okay. SOAP will allow you to do have n parties that all interact to carry out a task. Here you only have 2 parties that are interacting. So here's an example of a RESTful service. All this service is doing is it's actually making a query for the stock price of a company. Okay, so you send this as a GET request. So you say GET, you say /stock price, and you say IBM. Okay. This is the method you are invoking. Okay, so this RPC method gives you the stock price of a company. This is the argument that you are passing. Okay. This argument and the method are actually just standard HTTP URLs. Okay, so you may just say finance.yahoo.com/stock price/IBM. Okay. What will happen is that will go as a RESTful request. This is what is actually going to go. This is a standard HTTP GET request. Okay, so you'll say this is a GET. This is what URL I want. That's HTTP 1.1. I am the host. These are all standard HTTP terms. So nothing fancy there. This is a standard HTTP response that comes back. Every response is HTTP header. That's this. And here is what has come back. Okay, this says, here is the call you made. Okay, it's example.awk service. This is the method, this is the argument you send, which is stock price of IBM. Here is the response. Okay, this is the current value. Okay, so you make a RPC request over HTTP to get a stock price of a company, and the response comes back. Okay, so this is how you can write variety of different applications over HTTP. Okay, very popular. Okay, anytime you have a web API these days, this is basically typically a RESTful web API. Okay, so you can use that API to write interesting applications of your own. Okay, so just as an example, here is the same call that I showed on the previous slide if you sent it as a SOAP request. Okay, so you will see that the same request, which was just one line here. Okay, this is just this line has essentially expanded into a very large XML request. Okay, so you will basically say that's the XML envelope. This is basically the service you are trying to invoke. Here is the body of it. Then this is the argument. So each argument is encoded as an XML object, and then you send it. So it becomes quite bloated, and then you have to process this entire thing at the other end, and then the response comes back in this fashion. Okay, so this is what you invoked. This is the argument you send. This is the value that you are requested, etc. Okay, so you can write it the same thing using SOAP. Just becomes a little more complicated. Here, so this is what I was saying, is sort of a subset that allows you to do the right thing. So the thing to keep in mind is in this case, the argument actually went as part of the URL. Okay. In this case, the argument was specified separately. So here is an argument. Right, so here is the method, here are the arguments. In the previous case, all the arguments, they're all part of the URL. So it's much simpler to send it off. Okay, so these are some design decisions that these designers have made. Here is a slide that compares the two. Okay, so of course, there's RESTful Web Services. Okay, so they are both language and platform agnostic. Okay, SOAP is also transport agnostic. SOAP doesn't have to go over HTTP. Although that's a common way of deploying it, you can deploy it over other transport protocols. You can write SOAP directly over TCP, for instance. Okay. In this case, that request is going over HTTP. The transport is set. You can't send a RESTful web service request without using HTTP. It's embedded in HTTP. So that's the first simplification. We're assuming the request is HTTP, so you can simplify several things. Okay. This supports general distributed computing. N-party communication, each talking to one another is supported. This one is point to point. Okay, one machine making an RPC request to another machine. Standard what happens in standard RPC. Okay. This is standards based. There are definition language, there are compilers and so on and so forth. That is basically very popular, but is not a standard. Okay, you are just using HTTP and say, now we build our own RPC on top of it. Yeah, so you can define what the API is, how it works. It's completely up to the application designer. Okay, so they all look RESTful, but they will all be slightly different. So it's roll your own. There are no tools to write these services. You define, here is the API that I'm going to support over HTTP. Here's my implementation. You write the code yourself. Okay, so it has built-in error handling. It's extensible, etc. It's more heavyweight. As I said, this is simpler. Okay, so anybody who knows how to write web programs can easily write it. You can take PHP and may turn that into web services tied to HTTP, and it is more concise. Okay, so these are the differences between the two. This has become very common. Okay. This is still used, but I think is less common these days. This is basically the way any web service out there typically will look like a RESTful web service.
Arguments in SOAP and RESTful are only strings, or they can be like arbitrary data.
They could be arbitrary data, but typically they tend to be strings. Right? So Google Maps is another example of a RESTful service. Right? So it has a web-based browser, but if you have a tablet or a smartphone, you have a special Google Maps app. What that is doing is it's sending argument. Right? So in that case, typically the argument is the address. So in most cases, they tend to be strings of some sort. Although you could actually use it to upload, let's say you are using Instagram or some such thing to upload an image. Yeah, so you can embed that entire JPEG image as an argument and send it off, saying post this to my web page. Yeah, so that could be a blob in that case. Yes.
So the two methods are based on XML.
Yes.
So there are many vanity data in XML. Is that possible?
What's the question?
So is that possible to compress the data and make it more efficient? Because XML have many vanity data. They have had too many data.
Yeah, so question is, can you compress this XML thing? You could, but typically the other end expects ASCII text that it has to parse. So you will have to uncompress it and send it. So if you're just using HTTP, it won't go compressed. HTTP doesn't have an inbuilt compression. Okay, you will have to do something at a higher level. Yeah, so going back to the original question, you can have things other than strings. This is how you can post images and that kind of stuff. But the most common use is strings as arguments. Okay, so we have about 15 minutes. I'm going to go through the caching parts quickly. Okay, so now we are going to look at caching in the web and cache consistency. Okay, so from a client-server system, we are going to a client proxy server system. So what this is showing is a web server with some proxy caches. Okay, so these proxies are caching web content. They keep copies of web pages they have retrieved. So your browser can go to a nearby cache and say, give me the page for this site. Okay, so rather than going to a distant server, you go to a local cache. And the hope is if that object is cached, you can get it faster. So that's the advantage of caching. Okay, so rather than going a browser going to a server, the browser is going to a proxy cache. Okay, if the proxy cache does not have the object, you have what is called a cache miss. If you have a cache miss, you have to get the object, the requested page from the server, stick it into the cache and return it to the browser. If you have a cache hit on the other end, the requested object is already in the cache, so you can retrieve it and you're done. But the big problem with caching any content is you have to maintain consistency. Okay, if the page has changed on the server and you have an old copy of the page in your cache, then you have what is called stale content. Okay, if you then service users and send this old page, users will be unhappy. You can say that the actual page is different. You're giving me, like if it's a newspaper, let's say, okay, and you're giving yesterday's page for New York Times, and users are not going to get the freshest content, they are not going to be happy. So you want to ensure that any content that is stored cached here is consistent with what is on the web server. Okay, this is the cache consistency problem. Okay, the question is, and we looked at the semantics of how to do strong, weak, and all of that earlier. Now we'll look at protocols to do this. Okay, so now because this is web, we are going to look at some specific things that are actually true in the web and design our schemes or tailor the schemes to actually take advantage of. Okay, so we will assume, people have observed that many web pages are static. They rarely change. Okay? Some web pages are dynamic. They change all the time or they are generated on the fly. They are not even stored. They are generated on the fly. Right? So you go, let's say you go to the Amazon page. Okay, you will see your name is actually embedded. If you're logged in, it will say welcome and give your name. Someone else going to that web page will get a different copy because they may have their names and it's tailored based on what your shopping history has been. So no two users are ever present at the same page. Okay, so caching such content is hopeless because every user gets a different page. Can't cache it. Right? But you can cache static content, which is basically content that doesn't change very frequently. Okay, let's take the course web page for instance. I update it twice a week. Between those two updates, there is no change to it, rarely any change. So you can cache it for 3 days and keep serving that content, and when it changes, so the update frequency is twice a week. Okay, you go to CNN or New York Times, it gets updated, the breaking news section at least gets updated every few minutes. Right? So vastly different update frequencies. Okay, that means that the consistency requirements have to be also thought through very carefully. Okay. So there are different update frequencies going from few minutes to weeks and years. Sometimes people don't update their pages. Okay, so they don't get updated very often. Question is, how should the proxy cache maintain consistency? Okay, so there are two very canonical protocol ideas we are going to use. The first one is, whenever a page changes, how should the cache be notified? Okay, you can send what is called an invalidate message. That basically tells the cache page has changed, throw away what you have. Okay, and the cache simply discards any copy of the page. Or you can send what is called an update. In the update, you not only tell the cache the page has changed, you give it a new copy of the page. So here the page has changed, here is the new version of it. Okay, so you discard the old version and you replace it with the new version. Okay. So you have to think about when it makes sense to send invalidates versus when it makes sense to send updates. Okay, the basic rule is, if the page is very popular, go ahead and send that update. Because what will happen is, if you send an invalidate, the proxy will discard that object. Some new request for that page is going to come in because it's popular. That request will be a cache miss, and it will go back to the server to retrieve the page. So if that is going to happen with high probability, why not just send the page anyway with your invalidate message? Okay, that's an update message. Okay. So, and we'll talk about this in just a moment. The other option is, who is responsible for consistency. You can make proxy be responsible, saying it's your job, you figure it out. Or you can say server is responsible for ensuring that content and proxies or caches are consistent. Depending on which of the two, you will get a push-based or a pull-based approach. Okay, so those are the two dimensions we are going to play with. Yes, yes.
In the CD, would that mean that a server would have to keep track of whatever proxies have its content, whatever proxies have cached its content?
Okay. Question is, in a CDN or any cache, would you have to keep track of what the content is? Okay. Depending on whether it's the server job or the proxy job, the answer is yes or no. Okay. We'll talk about just that question in the next couple of slides. Okay. So who is responsible? What do you need to track? Okay. Let's start with the push-based approach. Okay. So here the server keeps track of every proxy that has cached our pages from it. It has to keep track of it. And anytime any of those pages are modified, it has to either send an invalidate or an update to those caches. Okay, so here is a server. There may be many proxies, not just one clearly. So you will assume that there are arbitrary numbers of proxies and there is a server here. There are of course many other servers, we'll ignore them for the moment. So whenever the proxy has actually requested any page from that web server, the web server will keep track. This proxy, this IP address has this page. Right? And if that page changes, the server is going to tell the proxy saying this page has changed. Either it will send an invalidate saying page changed, throw away old page, or it will send an update saying here is a new version, replace the version you have with this page instead. Okay. That's the server push approach. Okay. So if the page is modified, notify every proxy. And there are two kinds of notification. Okay. So you can either send an invalidate message, okay, or you can send this update. Okay. Now, question is, how do you decide between invalidates and updates? Okay, so as I said, it's better to send invalidate for infrequently accessed pages. Okay? Because invalidate message is a short message. It says this URL invalid. Throw the page out. Okay? Short request. Okay? Update is a much bigger message. You have to send an entire page or an image or whatever the object is with the request. So you're sending a much larger message. So the page is the object is not popular. You are better off as a heuristic saying throw it away, and if somebody happens to access it sometime in the future, come and ask me and I'll give you the new version. So I'm not going to do the extra work right now because I don't know if that work is going to pay off. Okay? On the other hand, if it's a popular content, if it's a headline, the home page of a very popular website, for instance, you are better off sending the new version of the page because with high likelihood that page is going to get requested very soon at that proxy. The proxy will come back to you anyway. So you may as well send with your push request saying page has changed, here is the new version. So simple heuristic is if you know the popularity or access frequency, okay, the read rates, and how many read requests are coming for this URL, then you can use that to decide whether to send an invalidate or an update. Okay. For high read rates, you use invalidate or an update. So now, yes, question.
In this, how is the web server tell the difference between a proxy request and a regular browser request?
Okay. Question is, how does the web server know the difference between a proxy request and a regular web server request? So if you are using plain HTTP to retrieve files, you will not know whether a browser sent it or a proxy sent it. Okay? But luckily there are other protocols. There is a protocol called Internet Cache Protocol, ICP, which essentially tells the web server that I'm asking for this object and I am a cache. So then you can keep track. If you're just using, if you're going to write over HTTP, I don't know if you're a browser or a proxy. And I'm not going to, certainly not going to tell every browser saying web page has changed. That doesn't make any sense, right? So you have to use special protocols, which I haven't talked about. I will show a few examples of that in 2 slides. So the advantage of a push-based approach is it provides tight consistency. It's sort of a form of strict consistency because every time a web page changes, you immediately notify all the caches. Okay? So only the message propagation delay is going to come in your way between the time at which the web page has changed and you're notifying caches. So caches will almost never have stale content except for the time it takes for the server to send messages. Okay? So it is a good form of consistency as far as caches are concerned. Okay? And all the intelligence has to be at the server. Proxies don't have to worry about it. They just request content, and if it has changed, they are told it has changed. So servers are smart, proxies are dumb. Okay? That's the advantage of the approach. The disadvantage of the approach, as you can imagine, is it makes the server stateful. Every proxy anywhere in the world that has ever asked you for any page, you have to now keep track of. And there may be lots of such proxies. You may have hundreds of thousands of pages. So you can imagine the amount of state you have to keep. For every page, you have to keep track of all the proxies that have ever cached that content from you. Okay, so this can actually become quite painful in terms of the state overhead. Okay? And because HTTP by itself is a stateless protocol, the way it has been defined, you have turned the server, which was inherently stateless, into a stateful server. Okay? And if your server crashes or you reboot, all this state, which is typically stored in memory, is gone. Okay? Because then you don't even know who has the content. You can't push notification. Only way then to do it is to actually keep a copy of that list also on disk, okay? Which also makes it slower and all. Okay? So this is good in terms of consistency, but implementation-wise, there are problems. Okay? You may have to keep this state indefinitely. Okay? Proxy asked for this page 3 years ago, I'm still sending updates or invalid. Doesn't make sense. Because in this protocol, proxy doesn't actually tell you I'm not interested. Okay, well, as soon as you start asking for a page, you are on the list. You are going to get notification, whether you like it or not. Right? So that's another problem. Okay? Indefinite, the state only keeps growing, it never shrinks. Yeah, that's a problem of that. We'll see how to rectify all of this. Okay? But before we see how to fix this problem, let's look at a pull-based approach. The pull-based approach, everything is switched. Okay? All the responsibility of cache consistency is on the proxy. Server doesn't do anything. Okay? So what the proxy will do is it will periodically, for every object it has cached, it will periodically poll the server. Has this page changed? The server can say yes or no. Depending on what it says, you can decide whether to discard what is in the cache or keep it. Okay, so this is a polling-based approach. You poll. Your proxy is entirely responsible. You periodically poll to see if the object has changed. You can actually use a special kind of HTTP. You can say, this is called if modified set, saying you can send a conditional get. It says get this page if it has changed since yesterday 11:30, because that's the version I have. Okay, and then the server can say not changed, still the same, or it can say here is a new version. So you can basically use standard HTTP to do this polling. You don't need anything else. Okay. Now the problem of this approach is that it's the proxy's job to decide how frequently to poll. A proxy doesn't know when the page is changing. Okay, that's up to whoever created the page. They can change it at their way. Proxy has no idea. Okay, some pages may change every minute. Some pages may change twice a week. If you start saying I'm going to ask every server every 5 minutes, that is very wasteful for pages that don't change at all. Or if you say I'm only going to ask once a day, that is too loose for if the page is changing every 5 minutes. Okay. So the main crux of the problem is to figure out how frequently to poll. And different web pages will have different update rates, and you will have to figure out what that update rate is and somehow poll for more popular pages more frequently and less popular pages less frequently. Okay. And the server is certainly not going to tell you this is a popular, this page gets updated frequently or not. Server is only doing HTTP. So here is a page, now you figure out what you want to do. That's on the proxy's job. Okay. Now there are some things that the server can do. Typically in HTTP, rather HTML, not HTTP, you can assign what is called a time to live value for a page. So a time to live value essentially is an expiration time. You can provide hints saying this is the time at which this page will expire. You can say expiration time is 1 hour. Okay, this is a hint you provide to the proxy saying very likely in the next 1 hour the page might change. Okay, so don't keep it for longer than that. Okay, so if such hints are provided, you can use that to figure out I'm going to poll after the expiration time. Okay? But the hint is only a hint, it's not a guarantee. Just because you specified a 1 hour TTL, time to live value, doesn't mean that the owner of the page cannot update it. Web server is not going to say, I told the cache it won't change for an hour, so you shouldn't change it. Right? You can do whatever you want, it's your content. Right? So it's only a hint, it's no guarantee. Right? So what this also says is that you have to decide the polling frequency dynamically. It is a looser form of consistency because the proxy can do its best to keep up, but it can never give you a guarantee that this page is up to date. Okay? The only way you can actually provide strict consistency in a polling based scenario is if you poll the server for every request that is coming in, even if it is a cache hit. Okay? You can go and say, I will never give you stale content. Okay? The only way to guarantee that in a pool based is request comes in, you say it's in the cache, but I'm going to check. So I go to the server saying, has it changed? If it's changed, then you fetch a new one. If not, you return what it. Okay? But if you poll on every request, the latency will increase because there's one more message exchange you have to do with the server. The whole point of putting the proxy cache close to the user is gone because cache hits were supposed to be fast because you can just return content quickly without having to go to the server. You have to check anyway, the whole point is gone. Okay? But that's the only way to guarantee strict consistency in a pool-based approach. You poll on every request. Okay? Otherwise, it becomes weaker. Okay? So I'm going to talk about this slide and then end. So there are schemes that people have developed where you can intelligently decide how frequently to poll. Okay? You can track how frequently the page is changing and then decide. So for instance, when you fetch a page for the first time, you know nothing about it. Okay, you say, I'm going to be aggressive and start polling every minute. So 1 minute after you fetch the page, you ask the server, has it changed? The server says yes. You say, okay, it seems to be changing every minute, you keep track. The server says no. Say, okay, it didn't change in the minute, so next time I'm going to ask after 2 minutes. Okay, so then you basically 2 minutes later, you go and say, has it changed? Again, the answer is no, you make the polling period even looser. Say next time, instead of 2, I'm going to wait for 4 minutes. Because you keep increasing this period, and you try to discover what the poll rate at which it is changing. Okay, soon you may be polling once a day, and maybe that's good enough. Right? So you will basically dynamically discover based on how the page has changed. So every time a page changes, you reset the value, and then you slowly keep increasing it so you don't poll unnecessarily. Right? So you can, this is referred to as intelligent polling, where you increase the poll interval if the object hasn't changed between polls, and you decrease it if it has actually changed between polls. Okay? So you can do this increase and decrease algorithm to figure out. It's fully adaptive. It doesn't need any prior knowledge of the characteristics of the page. You are discovering it by just polling and trying to guess based on whatever you are seeing, how frequently it changes. And you can just discover this in this fashion. Okay? So these kinds of techniques are used by proxies to be a little smarter about how they decide when to poll and so on and so forth. Yeah, so we run out of time. There is some a little more. I'll talk about advantages and disadvantages and stop there. So already mentioned that this is proxy based. The server is stateless. This is resilient to server failures. The server doesn't keep any state. Proxy also doesn't actually need to keep any state. It just needs to poll whenever it wants. It is a weaker form of consistency. There are no guarantees here. You may use tail content to your users. Okay? Because between two polls, the page has changed. Okay? No matter what that poll frequency is, until the next poll, you will have stale content. Okay? Unlike push-based, where you will get tighter guarantees. Okay? So you need smarter proxies. All the sophistication is at the proxy. There is no server. And you may have higher message overhead. Because polls are overhead that you are incurring. Server has to process it. Proxy has to process it. Many times the page has not changed. You are just checking and sort of increasing the burden on the server. Okay? So that's the disadvantage of this approach. So we'll stop here today. Next time when we resume, we will, which is actually in a little while, we'll look at how to take the push and pull approaches and combine them and actually get some properties that are the best of the two by eliminating the disadvantage. So, but that we'll have to wait for a couple of lectures. Okay? Just to recap the announcement I made at the beginning of the class, for those of you who came in late, no class on Monday. I am not here. I will have a makeup class once I'm back. And next Wednesday and the Monday after, we have two guest lectures. One on green computing, one on multimedia system. Yes, question.
Is the field trip still planned?
The field trip is still planned. I'm trying to coordinate with another group that is trying to also attach itself to the field trip. So if I can coordinate the two groups, we'll go as a larger group. If I cannot coordinate, I'm going to have it in the last week of classes. Okay, I will announce that soon. Because this coordination took some time, I haven't actually gone and set up it. But I am planning to, for those of you who are interested in going, planning to have that field trip to this local data center. Okay.